We're going to talk about refrigeration compressors today and the applications in which they're used. So in industrial applications, there's lots of needs for cooling things down below the temperature that you can achieve with cooling water. Cooling water generally will be in temperature ranges from about 80 to 100 degrees Fahrenheit. That's, I don't know, maybe 30 to 40 degrees Celsius. So in order to get things to cool down, you have to use some thermodynamics. So what we're trying to do is move heat from a low temperature to a high temperature, and the typical arrangement to do that is some type of a refrigeration cycle, generally based on the power cycles like Rankine or Carnot. So real quickly, just a review of the just a quick review of the thermodynamics. We'll have a looking at a temperature entropy diagram. We would have it's ambient temperature, maybe 40. Well, cooling water will be warmer than ambient, so we'll say that's a 40-degree temperature line, and we want to cool it down to maybe minus 20. And so that would give us these are the targets. So this would be our minus 20 here, and this would be 40 Celsius. Okay. Now to get well, let's draw the pressure line. So on a for the compressor, if you had a saturation zone, the temperature and pressure are coincident, but as you move away into the superheat region, you'll have a line that does this. The other pressure line would be similar, coming off at the high pressure. So our the operation of the machine would move, we would take suction from down here at the low pressure corresponding to the saturation temperature of minus 20, and if it was an isentropic compressor, you'd get an isentropic line that looks like this. It'd be a vertical line. That's ideal compression, right? So then if it's not ideal, the ending entropy would be maybe over here to the right just a little bit. So our ideal line, I mean actual line, would look like that. We'll make that one yellow, and so we would compress from the low pressure at suction up to the high pressure, and of course it comes out at some higher temperature because of the heat of compression and the inefficiencies, but we run that through a cooling water exchanger at the high pressure, so that cools down the superheat, and then if you continue to cool it, you'll bring it down to the saturated liquid line on the left side of the dome. So we move from low pressure, low temperature, to the discharge pressure at high temperature, cool it down to a saturated liquid, and then if you look at the constant enthalpy lines, they look something like this. They come off at an angle So our if you let it down through a valve, if you expand through a valve, that's a constant enthalpy operation. So as we expand the liquid, saturated liquid down to the low pressure to bring it back to the low pressure exchanger that we're trying to cool, we achieve the lower temperature along this with this isenthalpic drop. So that's the complete refrigeration cycle. We would heat up from this point so we heat the gas up. We heat the saturated gas by passing it through the heat from the process will heat up our liquid. So this is a saturation zone. So within the exchanger, in the shell side of the exchanger, you'll have liquid sitting in the bottom that covers up the tubes. The tubes have whatever your process gas is in it that you're trying to cool. So in the shell, our exchanger would have this two-phase propane or propylene liquid sitting on the tubes, and then the vapor rising to the top where it's sucked away by the compressor. So the vapors would be on the saturated vapor line, and that's where they're sucked into the compressor and go back up to the discharge where they'll be cooled and condensed again. So the heat that we get from the refrigeration process, or the cooling that we would get, would be basically this what we get from this two-phase, the absorption, the area under this curve. So you put a bunch of work into it and you get a little bit of it back to cool your process. So that's the thermo, real quick. So we need to look at to see how a compressor might do that. Now, the simplest system would be just a single stage compressor that takes the heat from the evaporation process, compresses it to high pressure, then it's cooled in an exchanger and comes back around. Let's look at how that might look. Okay, let's draw a picture of the process that we just described. So we've got a compressor. We'll have a we got to make an evaporator, and what it is what they look like is a horizontal vessel with a nose on one end, and it would basically look something like this. The nose can be on both ends actually, so it depends on what kind of exchanger it is, but it's a large horizontal vessel with tubes running through the bottom, maybe half of it. So that nose sticking out on one end is the collection box, the header for all those tubes. So it's if the nose is just on one end, then it's a split box. In other words, the tubes, the external piping would come in and out of here, and it would be split horizontally, and you would have a bundle of tubes in the bottom that would turn and go back and come out in the other half of the collection box or the header. So a typical arrangement would be you would have a pipe coming in the bottom, that would be, you know, the incoming warmer liquid or gas. It would pass through tubes in the bottom of the shell and turn and come back, and so this this box would be basically split in the middle, and then the gas would come out the top. So it's just an empty collection area with a tube sheet, and then it comes out the top to go on to. So you'd get, I guess if it was a gas, it may go the other direction, so the liquid would come out the bottom. They can do them either way. So gas comes in, liquid comes out. If you did everything right, it doesn't necessarily have to condense. It depends on what your cooling is. So then there would be a liquid level over the top of the tubes inside of the drum, and vapors come out the top. So on our condenser, now with a with these condensers, I mean these evaporators they call them, it's an exchanger that evaporates your refrigerant. You generally don't want to go directly into the compressor with that. You want to make sure you've got good liquid knockout, so they've put a drum upstream of the compressor, downstream of the evaporator. So we would have a vapor line coming off of the evaporator, and then out of the top of the drum you would have a line that carries the vapors into the compressor. Now after the discharge of the compressor, we would have an exchanger that cools the vapor, and cools it all the way down to a liquid. So there would be liquid coming out of our exchanger. We want to collect that, and so we put a drum underneath here we call an accumulator. So let's put some quick labels on here. We'll call this as the evaporator. This is our compressor. This would be our beat this thing. This is a drum, knockout drum. This we'll call the condenser. And this one is the accumulator. Okay, so now we've turned it into a liquid. What do we do with it? Well, we've got to get it back to the evaporator. So the evaporator, as it's cooling our process stream, it's evaporating our refrigerant. So the level of liquid in this evaporator will drop as we put heat into the refrigerant liquid. So the evaporator will have a level controller on it. So we'll just draw a little bubble here and call it a level controller. And then that would be, you know, on a bridle or something that would measure the level in this in the shell side of our exchanger. Okay, so the level controller will then operate a control valve that would monitor that would modulate to control the liquid level. Okay, so off of this valve would be fed by our accumulator, and feed back into the evaporator. Okay, so that's pretty much the complete loop now. We have a compressor that pulls the vapors off of the drum. The vapors are created by the heat added to the liquid in the evaporator from the tubes that are submerged in the liquid. That vapor passes into the drum. If there's any entrained liquid, it'll drop to the bottom so that we don't suck it into the compressor. The compressor then delivers high pressure refrigerant to the condenser. The condenser will then turn the gas into cooler liquid. The liquid has some hold up in the accumulator, and then is passed back into the evaporator by a level controller that maintains a level to keep the tubes submerged in liquid in the evaporator shell. When you let the pressure down across this valve, it doesn't immediately get cold. You have to well, it gets cold by flashing off part of the liquid into vapor. So when you drop the pressure of the refrigerant, when you drop the pressure of the refrigerant from high pressure down to low pressure, it doesn't want to be the liquid can't remain as liquid at the lower pressure, so it starts flashing off, and as it flashes off, that it removes heat from the remaining liquid, and eventually that liquid gets cold enough that it's no longer at a temperature that wants to drive it into a vapor state. So up here we're at a high temperature. So when I say up here, when we're up at on the saturated liquid line at high pressure, we're at a high temperature and pressure. When we drop to a low pressure, at the temperature that this liquid was at, it cannot stay. The saturation pressure is too high, so it will try to evaporate. But as it evaporates, it needs heat to drive that phase change, and the heat is pulled from the remaining liquid that hasn't flashed off yet. So you wind up with a low temperature liquid eventually when you get down here, but in the process you've used up some of the energy that you put into the liquid to get it into liquid state, you've lost it, and it becomes vapor. So the vapor doesn't do any good for cooling. There's not enough specific heat in that vapor, so it just rises to the top of the drum, the evaporator drum. It's boiling inside of there. Inside there's a bunch of bubbles going up to the surface. They break free and into the vapor section of the drum, where they're pulled away by the compressor.